Welcome back to Introduction to Material Science and Engineering. This is our third and last lecture for the Callister text chapter 7, Mechanical Properties. And we're going to go over viscoelasticity, which is particularly applicable to polymers, but applies to other materials, especially at high temperature. And we'll finish up our treatment of mechanical properties with a discussion of safety factors and working loads, and how to make sure that we relate real capabilities of materials on all the things we don't know about a design to ensure safety. So viscoelasticity is otherwise known as time-dependent deformation, and it literally combines the load versus constant strain rate of viscous behavior or fluid movement, and that being related by viscosity, and elastic behavior, which we just discussed the lecture before last with an elastic modulus relating stress and strain. So you have a material that is deforming and it's simultaneously trying to behave elastically, where its stress will be directly proportional to its strain, but it also wants to behave like a viscous material where its stress will be proportional to its strain rate, which is almost like the ultimate plasticity. It's literally flowing. And so this typically arises from materials that have a microstructure which supports both, and polymers are definitely the big examples of that, and this comes as a result of the amorphous portions of their microstructure, even a crystalline polymer being partially amorphous, and then the crystalline portions being more likely to behave elastically and the amorphous viscously. But even all amorphous polymer will have portions of its bonds that want to act like a spring and act elastic, and that would be the chains themselves being loaded along the polymer main chains, and to the extent that chains want to slip past one another, the spaghetti pile, that will cause a viscous flow. So any way you look at it, polymers have the capability to behave differently. So how do we quantify this? I mean, good heavens, we're going to run a stress-strain curve, and what do we measure? How do we find a modulus? How do we find a yield point? You know, how do we design something where we have to apply a load? What is it going to do? Is it going to yield differently if I come back in 2 days versus 2 minutes? And the answer is probably, actually. So we need to take time into account, and loading rate and temperature with these types of materials. So we have to be prepared in many cases to do a lot more testing. So we need to understand how they behave under all of these different circumstances. So in order to not spend our whole lives in the test lab, we've evolved different mathematical models to describe viscoelastic materials so we can zero in on the tests under the conditions that we're going to need in the field. And this is one way to look at one of the models that we're seeing on our slide here. So in this case, we are looking at what would happen if we took a material that's viscoelastic and we applied a load. We went from an unloaded state on our red curve on the upper left. And so at time TA, T applied, for we applied the load at that time, we applied a load, and the load jumped up, and it was constant, and we held it for some time until TR, meaning T release. Well, if the material was an elastic material, like a metal that was loaded to a stress that was below its yield point, or most ceramics, or say a thermoset network bonded polymer, or anything of that ilk, you would get a strain that basically had the same shape as the load. And the difference in the levels of that flat center portion in the elastic blue curve on the upper right and our red load curve ratioed to area would be the elastic modulus. So the total achieved load versus strain ratioed to area, which wouldn't be changing that much because it's elastic. If it were a viscous material like a fluid flowing, so we were looking at putting something, in this case probably in shear compression, like a tube of thick molasses or honey, or maybe a polymer melt coming out of an extruder, and we applied a load over time, we would notice, and we measured just strain, we would notice there was obviously no strain until we apply the load. And then from the time we apply the load at TA, looking at the yellow curve in the bottom right, for the same load, no increase in load, constant load, we would get a strain that increased linearly with time until we release the load. We would not recover any of that strain. It would all be permanent. And so that's following stress equaling viscosity times strain rate. Now, most polymers, as we discussed, are some combination of the two, and that's the green curve on the lower left. So in this case, at the time we apply the load, the elastic mechanisms within that material allow it to instantaneously deform elastically with a modulus, a Young's modulus. But over time, the mechanisms that allow for viscous flow start to take over, and we get that time-dependent, definitely less steep time versus strain. And then when we release the load, we recover the elastic portion, and then we start to recover some of the strain. So we get sort of a sawtooth type curve. So that would be the result of our test. So what are some trends that we tend to see for viscoelastic materials? We'd said it's obviously time dependent because we just did this whole test with respect to time. The two other main variables that are important, and we touched on strain rate a little bit with just noting that our viscous mechanisms or viscous strain was dependent on stress versus strain rate. That was the viscous relationship. Viscoelastic material behavior, its stress strain behavior, will be very dependent on the temperature at which you run the test, or the behavior of the material in service will be dependent on the temperature of your service environment. With decreasing temperature, so colder, giving you effectively a higher modulus, a higher effective tensile strength, and a decrease in effective percent elongation. And you can see that on the graph over to the right, which are stress strain plots for semicrystalline polymethyl methacrylate. So at cold temperatures, 4 degrees C, it behaves almost like a ceramic. It's the upper sort of royal blue line. No plasticity, no viscous flow. Room temperature, we get a little bit of a combination of both, slightly more effective lower modulus and a little bit more elongation at 40 degrees C, and then almost full flow at 60 degrees C. And so we will define something very important that happened to that material between 40 and 60 degrees C called glass transition, where the material went from behaving rigidly to flowing or behaving like a rubber. So the higher elongation that we're seeing in this plot is telling us that. There are other tests that call that out much more specifically, and we'll go over a couple of them. So in addition to changing temperature, we can change loading rate or strain rate. So the faster we apply a load, or the faster we force something to deform, the faster we yank on it, not necessarily harder, but faster, will have exactly the same effect as decreasing temperature. Colder and faster have the same effect on viscoelastic behavior. So if I force something to deform very, very quickly, it will act as if it's very rigid with a high modulus. It will tend to display a higher strength and much, much lower elongations. So we can look a little bit harder at our time-dependent deformation for viscoelastic materials, and we can think in terms of what's called a stress relaxation test. So instead of applying a set load and looking at how a material deforms with time, we can yank the material, pin it in place, or compress the material and hold it in place, and therefore define the strain. We can impose a set strain and then see what happens to the stress in that material over time. So if we think about maybe a polymer or a rubber, we yank it out to a given strain, pin it in place, and then over time we see how hard does it keep pulling back, and measure that as a function of time. So if we do that measurement, we can define a modulus and that's defined down on the lower left-hand side of the slide, called the relaxation modulus for this particular test condition. This is only for a fixed strain test, and it's defined as the time-dependent stress over the original strain. So again, we're gonna strain it to some original strain, which could be pretty big, and then we're going to look at the time-dependent stress within that material. How hard per unit area does it pull back? This is not to be confused with Young's modulus, because this is definitely including a lot of very, very permanent deformation and plastic types of mechanisms, viscous flow. So even though it's a capital E, it is not Young's modulus. It's the relaxation modulus. It's what we call a pseudo-modulus, merely meaning that it is a ratio of stress and strain, but only a portion of it is elastic. It's a combination modulus. So if we measured that ratio as a function of temperature, again for another polymer, amorphous polystyrene, which is most polystyrenes, by the way, steric hindrance, preventing crystallinity, and we looked at that as a function of temperature. So we had mentioned higher temperatures tend to give you lower modulus and lower tensile strength, etc. So we're going to measure relaxation modulus. We're going to repeat this test again and again at different temperatures. We would find that at, room temperature, higher than room temperature, 60 degrees C, we're getting fairly high relaxation modulus. And this is, again, because it's time dependent. We're defining that time here as at 10 seconds. So what's the stress for our original strain at 10 seconds as a function of temperature? So we'll start out looking at that value. It starts out as being about 1,000 stress units, so 1,000 pascals. In this case, it's megapascals. So 1,000, so it would be 1 gigapascal if we're around 60 degrees C. But if we get up around 80 degrees C, we see a big, fast drop with temperature of our 10-second relaxation modulus. So over a fairly narrow temperature range, we drop that modulus by several orders of magnitude. And we hit a plateau and then dropped again. That first drop is known as the glass transition temperature, and it's probably one of the most important material benchmarks for polymers and other viscoelastic materials. It is unique to something that's amorphous, and it defines the temperature at which something will go from behaving like a rigid solid to behaving like a viscous solid or a rubber. And anything that has a significant component of amorphous material will have one of these. Polymers all have enough amorphous material to have a glass transition temperature, even if they have a high fraction of crystalline materials. The crystalline portion of the polymer can still melt. So you can have a melt temperature and a glass transition temperature, both. But the glass transition temperature will be lower in almost every case, and it will therefore, because it's lower, it's going to define the useful material properties. So glass transition is definitely the big temperature-dependent mechanical property that we're concerned with in polymers. And it's, again, a result of the onset of those viscous or time-dependent plastic deformation mechanisms that are unique to polymers at those low temperatures. Metals would do the same thing again if we got them hot. And though they would undergo viscous flow with a very different mechanism. It's called creep, and it's the sort of the crystalline analog to viscous flow. It's where dislocations can move in the orthogonal direction to the way they normally would, and move very fast and not get tangled up. And it's actually the mechanism that we'll use for some of our annealing processes. So it's all related, but viscous flow in metals, you have to get them definitely above 1/3 of the melt temperature, and so it would be mainly for high temperature applications where we'd want to design against it, or for processing if we needed to form at high temperature. A little bit more about glass transition. It actually has some thermodynamic implications if we're looking at a full up phase change. If we scan our temperature and look at heat flows in and out of a material, if you've taken, remember thermo from your physics or chemistry, you'll get quite a bit of heat or energy flowing into or out of a material as you undergo a phase change. They're isothermal. So all of the heat energy is going into changing the phase, not raising the temperature of the material. And so that would be what we would get on the left-hand side of our blue shaded box. If we were melting a material, as we increase temperature, we'd have a linear relationship between heat flow and temperature, and then we'd reach a point where we'd start melting the material. We would keep pouring heat in. Temperature wouldn't change until we'd melted the material, and then the material temperature would continue to climb, probably on a different slope because now we have a liquid. If we looked at glass transition with the same kind of scan in temperature and then measuring heat flow, we wouldn't get a jump in the line, but we'd get a slope change. And this is called a second order thermodynamic transition. So we can actually look at plots of heat flow as a function of temperature change with a method called differential scanning calorimetry. And that's one of the ways that we can measure Tg for a given polymer and then use that information to understand when we're going to get, at what temperature we're going to get these dramatic changes in mechanical properties and design around them. So again, just other hints, tips about Tg. Again, it's applied only to the amorphous portion of polymers. So for an all-amorphous polymer, it would apply to every bit of the polymer. For a semi-crystalline polymer, that glass transition is only going to apply to the amorphous portion, which will probably be at least 20%. So, and again, it will typically be the continuous portion of the polymer. So even if it's not much by volume fraction, it will control properties. So doesn't matter if your polymer is 90% crystalline. If your glass transition temperature is at 80 C, it doesn't matter where your melt temperature is. You're going to design your mechanical properties around 80 degrees C, as in don't get it close to that or it will flow. Okay, well, what happens if you need to increase or decrease Tg? Because maybe you have to design around a given temperature and you don't have any choice. You have to use it. You have to use a polymer. You can increase glass transition temperature by cross-linking. That won't let chains slip past one another. So if we don't have chain slippage, we don't have viscous flow. You can increase the molecular weight, increase chain entanglement. It's not as effective as cross-linking, but it will help. And you can maybe maybe stop short of a full cross-link, but have some interchain secondary bond, some secondary bonds like some dipole-dipole that we saw in nylon, interchain, or some thermoplastic elastomers, maybe some hydrogen bonds between chains. All of those will tend to increase Tg by preventing chains from slipping past one another. And in the case of cross-linking, it will completely preclude it. To decrease Tg, go the other way. Reduce molecular weight, don't cross-link, and you can go a little further, get the chains further apart by adding plasticizers. It's very possible to add a plasticizer unintentionally, such as letting something soak up a little bit of water. So that's a really big thing to look for if you have especially a polar polymer like nylon. It can absorb moisture. The moisture will act as a plasticizer, give you a lot more free volume between chains, and while it might not show up at a zero-time instantaneous mechanical property, it could reduce Tg and show up at temperature. Just a note to correct myself a bit. While cross-linking will definitively preclude chain slippage, in the case of thermoplastics, it will prevent chains from completely slipping past one another. A cross-linked polymer or even a full network polymer could still display a glass transition temperature and have a change in properties, but it won't undergo full viscous flow above Tg. it will display what's called a rubbery plateau. So its fracture toughness will increase, its rigidity will decrease, but it just won't flow because the crosslinks will prevent that. So didn't want you to think it didn't have a TG, but you won't necessarily get chains completely slipping past one another if you crosslink. Okay, design and safety factors. Why do we use safety factors? They basically lead to us having to over-design. Many of them are specified by law, by statute and code. They're very important. The reason we have safety factors is we can calculate loads, we can calculate stresses and strains, but there are many, many things about designs and materials that we just can't ever know. Starting from the bottom, microcracks and voids. Materials aren't perfect. We talked about dislocations and grain boundaries, which aren't necessarily deleterious, bad defects, but they control material properties. We can get real defects, processing flaws, things that will definitely compromise the strength of a material that you don't know is there. The whole field of non-destructive evaluation and testing is intended to show those up, but no inspection method is perfect. The other thing that's not shown on this slide is how your customer might use your material. Just because somebody says they're going to take it to a certain temperature doesn't mean they won't inadvertently overcook it. Maybe people don't know exactly what their loading is. Maybe there'll be a loading factor that no one had counted on. Sometimes even a big safety factor won't account for that, but it at least accounts for a certain amount of human uncertainty in a design. For your supply chain folks or business people buying materials, probably one of the biggest things you need to understand is that published properties usually correspond to the statistical mean of what the vendor tested. So now you got two factors of uncertainty. What did they actually test? How long have they been producing this material? How big is their statistical sample? How big is their N? And then what they publish is usually the mean. How broad was that distribution? Because guess what? You better be designing to the minimum. What's their 3 sigma? Could be a lot lower. So using a safety factor just accounts for all of this stuff that, while it may be possible to find out, it's not always practical to find, and in some cases, might not even be possible. And so a balanced approach to design and safety factors is not to assign so high of a safety factor that your design is impractical, it's too heavy, that can have energy consumption consequences today as well as cost, but certainly isn't unaffordable. But you also don't want to under-design to the point where one of these unknowns can rear its head and cause an in-service failure. Okay, so all that. What is a safety factor? It is literally the ratio of the calculated stress, what you think you need, and what the design stress is. And it's always a number larger than 1. So if you calculate that you need 100 psi for a given material and you want to assign a safety factor of 2, you would not allow a design stress more than 200 psi. So it's what you calculated that you needed and then what you allow. So in that case, you would not select a material that gave you less than 200 psi for whatever stress that was, which in this case would probably be yield. So working stress just simply goes the other way, but it's approaching it from the standpoint of something that you really want to avoid, a critical stress. So say you knew that you had a yield stress or a fracture onset type of stress of 1,000 psi. You would not allow a working stress that was more than that 1,000 psi divided by your safety factor. So in this case, the working stress would be a smaller number. So in this case, the design stress on the top is what you're designing the material to meet the calculated need. So a higher safety factor means you get a stronger material, and working stress means you're going from the basis of a material can take no more than a certain amount. you're dividing by a higher safety factor, which means the applied working load drops. And that's something that you can work out with some exercises. And that concludes our lectures on mechanical properties. This is the last of 3. We will move into strengthening mechanisms with the next lecture. And as a warning, since these were fairly calculation and application heavy concepts, please be prepared to review the book and work any kind of graded exercises that you might have received, because that's how you'll really lock these concepts in and make them real. It's like a bit more like a math class for this chapter. You'll have to do the problems to really get it. But it will be worth it as we dive into future chapters, because you'll be able to use these concepts to truly fabricate and design real materials and then work to keep them from failing in service, which we will hit next time. Thanks.